All right, welcome to the video on ellipses. Ellipses are a little bit weird, so I decided to make a video so that you can look back if you ever need more help or forgot, things like that. So starting off, I want to start with this video of an ellipse. So remember, we're thinking about our graphs right now as locus points. So we're trying to think of them as a group of points. So watch this video and try to think about how this oval is being represented by a group of points sharing one characteristic. So, pause. So notice the oval is being made by analyzing this. The oval is being made to this with the same one. Blue is, and so you can see as this floats oval, sometimes blue is, that would require. Looks like when the distance. So from two foci equals some number. So let's go back to our notes and fill this in. An ellipse is the collection of points, aka a focus, right? Not a focus, oh my gosh, locus. My bad, let me do that in another color. This is a locus, a group of points, a collection of points. So what characteristic do they share? They share that the sum of the distances from 2 points is some number. So I gave you the example of 10, but it's not going to be 10 every time. And remember I said these 2 points are called focus points, or for plural foci. Collection of points where the sum of the distances from 2 points is some number, right? So this is the group of points that these 2 distances add up to some constant number, some number. Let's dive a little bit deeper. So this is an ellipse, right? This is an oval. Obviously, the oval is stretched further horizontally. So see how it's obviously more spread out among the x-axis? So we would call the x-axis the major axis. And we would call the y-axis the minor axis. So if your oval is this shape, this is your major, this is your minor. Let's jump ahead though. Now my x is minor and my y is major. So it depends on the orientation of the oval. Next, more terminology. We call these points my minor vertices because they're on the minor axis. And we call these my major vertices. Awesome. So the only thing that we have missing are the foci points. So again, individually they're called, that's not symmetric, shinners. Try to make them symmetric, right? So they should be, no, it still doesn't look great, but you get the idea. So our foci groups, foci, or that's the plural of focus. These are my focus points. And those are the points that I'm calculating the distance from. And now let's attach some letters. So whichever axis is your major, we call these points, we just use the letter A. So that's easy to remember, right? Major, you use the letter A, comes first in the alphabet. So this would be negative A0, right? And then up here, for the minor vertices, we always use B. And for the foci, we're going to use the point C. So this is C0 and this is negative C0. So A goes with major, B goes with minor, and C is for the foci. So let's do some general notes. The center of my ellipse is 0, 0. The major axis is dependent upon the longer side of the ellipse. Also, I have an equation relating A, B, and C. It looks a little familiar, but it's not quite the Pythagorean theorem, so be careful. So here is the equation relating A, B, and C. So it's B squared equals A squared minus C squared. And the proof for this is very long. I really wanted to do it in class, but it's really long and pretty complex. But I will say that one of the tools used in the proof is the Pythagorean theorem. So that's where the general setup comes through, is using the Pythagorean theorem to prove this. And if you're interested, I would really urge you to look this up because it's a cool proof. Similarly, if we wanted to solve for different variables, couldn't I solve that and get C squared plus B squared equals A squared? Right? If I add C squared to both sides, and then what would happen if I subtracted B squared from both sides? I would get this. So those are just different versions of the same equation, and based on the information you have, you might want to use all or specific one, right? The other thing I want to point out, and I mentioned this, but A is always bigger than B, right? So A is always on the long side of your ellipse, and B has to be bigger than C. So C should be the smallest all the time. So if this isn't true, you probably made a mistake. Let's move on to the general equation of an ellipse. And it looks similar to a circle equation, but it's a little bit different. And how it's different actually tells us a lot about ellipses. So here's the general beginning of it. And then we actually divide. And we divide by the vertex on that axis squared. So let's see here. What goes under x squared? I look at my major axis, and it looks like I have A0 and negative A0. So it would be A squared under the x squared. And then under my y squared, I go on the y-axis, and that's obviously b, so it's b squared. And that's going to always equal 1. So that's the other weird thing about ellipses. They should always be bigger than, they should always be equal to 1, not bigger than 1. Cool. Let's see how this looks in our second one now. So this one's a little bit different, right? Our minor axis is on the x-axis. So that would mean that this is now my b, And this is now my A. And then my foci are always on the major axis. So now that the major axis is on my Y, then my foci change to be on my Y as well. So this would be 0, C, 0, negative C. One point I will make is Y-axis is the major axis now, because the Y-axis side is longer. So it depends on what's longer. What longer side is on which axis. That's horrible grammar, but I think you get the idea. And then let's remember our handy equations here. So these still work even if the ellipse is on the other side. And then I think 8 squared. So those are the same equations as above. I'm just rewriting them. So it's always this setup, and then I just have to figure out what to divide it by, okay? Now my x-axis has the b, so this is now b squared, and my y-axis has the a, so now it's a squared. Cool. Let's look at an example here. So find the vertices and foci. So let's start with finding the major vertices. So the major vertices are going to be the vertices on the major axes. So it looks like since 9 is bigger than 4, it looks like my x-axis is going to be the major axis. So that means my vertices are going to be 3, 0 and negative 3, 0, since this is a squared. And my minor vertices are going to be 0, 2 and 0, negative 2. Why don't we go ahead and graph that? 1, 2, 3. So these are my major vertices. And then 2 out here, minor vertices. And now let's figure out my foci. So to figure out the foci, we have to use our equation. So I figured out that A is 3 and B is 2. So we have to solve for C, right? So let's look back at my equations. I'm going to use this one, right? Because I'm trying to solve for C. So I'm going to write that down right here. C squared equals A squared minus B squared. And plugging in my values, I'll get 9 minus 4. So I'll get the square root of 5, which is just about 2.4 for graphing purposes. So my foci are going to be along the x-axis, since that's where my major axis is. And this is what I get for my foci.